This is Algebra 2, Chapter 0, Section 6, in which we are multiplying probabilities. This is different from what we did last time where we were adding probabilities. This time we are looking at multiplying things that are going on. Before we start that, we need to know about the different kinds of events we're looking at. If one event has absolutely no bearing on the other, then it's called independent. Something like flipping a coin and drawing a card. The deck of cards doesn't know whether the coin came up heads or tails. It has no effect on it. If you have something where one thing does affect the other, then they're called dependent. That would be a situation like drawing two cards from a deck and keeping the first card. Now there's a different deck to work with for the second card. It's changed. Okay. If the two events are independent of each other, then all you have to do is multiply the two events together separately to find the probability. Probability that both events happen is the probability of each one multiplied together. So let's toss a coin and roll a die. Question is, what is the probability that the coin will be heads and the die will be even? They have no impact on each other, so this is an independent case. All we have to do is find them separately and multiply. And that's the same thing in symbols. Probability of tails and an even is the probability of a tail times the probability of an even. Well, the probability of getting a tail is 1 out of 2. It's either heads or tails. The probability of an even is 3 out of 6, which reduces to 1/2. There's 3 even numbers out of the 6 numbers on the die. Multiplying together, we get 1/4, or 0.25, or 25%. Those aren't so bad. The dependent events are the ones that you have to think a little more about. You have to look at conditional probability, the probability that one thing happens based on knowing something else happened first. Typically, you're looking at things where you draw without replacing. As I said earlier, if you draw 2 cards but you keep the first one out, now you've got a different deck. Or a different bag of marbles or box or whatever. If you don't put back what you drew, then you're looking at a dependent event, so it's conditional. In this case, the probability that both things occur is given by this mathematical formula. The probability of A and B is the probability of A times, and the way you read this is the probability of B given A. Probability that B happens given that you know A already happened. Okay, sounds a little complicated, but you'll get it pretty quickly here. Okay. We have a bag of marbles. We have 12 red marbles, 9 blue, 11 yellow, and 8 green. Okay. If we draw 2 marbles out at random, and we don't replace as we go, then what's the probability we get a red marble followed by a blue? Since we're not replacing, we're looking at a dependent situation. We know there are 40 total marbles in the bag. 12 of those 40 are red. So the probability on the first draw is getting 12 out of 40 for red. Now I'm holding that red marble. So now there's only 39 left. 9 out of 39. So the probability of a red followed by a blue is 12 out of 40 for the first draw times 9 out of 39 for the second. And my calculator tells me that's 9 out of 130, or 0.069%, or 0.069, or 6.9%. Okay. I'd like for you to pause here and try this one. You've got your note sheet in front of you. We're going to use the same bag of marbles. This time your goal is to find the probability of drawing a green, and then a yellow, and then another green without replacement. So pause here, take a look at it, and then we'll check it out as we go. Okay. Probability of green, then yellow, then green. There were 8 green out of the original 40. There were 7 yellow out of the 39 that are left. And then there are only 7 green left because we kept one out of 38. 49 out of 7410 if you write it as a fraction, or 0.007, or 0.7%. Now, using the same idea, we can do a little rearranging to divide out. They're going to ask us some problems where we need to figure out the probability that A happened to start with, or a probability that B would happen given A, I should say. So that they're going to give us the probability that both things happened, and we'll have to work backward, is what it amounts to. Okay. Kind of a tricky idea. Takes a little getting used to. But the probability of B given A is equal to the probability of A and B together divided by the probability of A to start with. So we're looking at this situation. We have a restaurant where 25% of customers order chili, and 4% order both chili and a baked potato. I want to know the probability that I find someone, if I know that they ordered chili, will they also order the baked potato? Okay. I'm going to rewrite our formula in terms of what's in the problem instead of B and A. I want to know the probability of someone ordering a baked potato given that they ordered chili. And that's going to be the probability of getting both things divided by the probability of getting chili. Well, we know the probability of getting both things is 4%. Probability of getting just chili is 25%. So 4% divided by 25% gives us 0.16, or 16%. A little different way of thinking about things. Working backwards to divide out to get back to where the conditional probability is. Same idea works if they throw it at us in table form. Okay. We have a drug company testing a new miracle pill for the common cold. So we have some people that we treated with real medication and some that we just gave what's called a placebo, where there's nothing really in it. So those are our two groups. We have people who improved in each group and people who didn't improve. Okay. When I get a table like this, I love to get the totals. It makes life a little easier for me if I have the totals. So there's 2,000 people in each group, treated and not treated, for a total of 4,000 people in the study. 2,800 people total improved. 1,200 in total did not improve. Okay. So I'm going to pick somebody at random, and I want to know what's the probability that his condition improved given that he received treatment. Okay. So what they're asking me is the number of people who were treated and improved out of the total number of people treated. There were 1,600 people that were treated and improved. I'm going to jump back and show you. Treated people who improved, 1,600. And there were 2,000 total people treated. So the probability is 4/5 or 0.8 or 80% that if I pick someone out and find out that they improved, were they treated? Okay. So a little bit of a tricky concept there at the end. We have to work backwards, but I think we can handle it. If you had questions along the way, hopefully you jotted those down as always, and we will see you in class.